Presentation 10 is the third and final presentation dealing with the timer counter. Prerequisites for these presentations are my presentation number 8 and my presentation number 9. As usual, I like to start showing the architecture, our architecture I should say. In green are the items that I've already presented. In yellow is what I'm going to be presenting today, which is the timer counter. Now the timer counter belongs to our layer 2. So the agenda for today. So I will be talking about pulse width modulation, definitions, and sample programs. And I'm also going to be talking about input capture, definitions again, and sample program. So let's get going. Let's start with the pulse width modulation. And there are two parameters that we need to consider when talking about pulse width modulation. One is frequency, and the other one is duty cycle. Let's start with frequency. Frequency refers to how many pulses are being transmitted in 1 second, and that's measured in hertz. So how many pulses per second we're putting out. The duty cycle has to do with the shape of the pulse. What do I mean? Duty cycles refers to the percentage of time the pulse is high versus low. It basically, the duty cycle refers to how long the pulse is on and how long it's off. It is expressed in percentages. So let's start talking about the signal frequency. The frequency of the pulse width modulation is determined by 3 parameters. The first one is the system clock, which in our case is 16 megahertz, the prescaler value, and the maximum count value of that the timer can reach. So the frequency formula is as follows. It is system clock divided by prescaler times maximum count. The maximum count for timer 1, which is the 16-bit timer, is 65,535. The maximum count for our times 0 and 2, which is our 8-bit timer, it's 255. So let's go. Let's go through some example calculation. So let's do the calculation assuming that we use a prescaler of 64. So for the 8-bit timer, the frequency would be 16 millions, which is the our clock frequency, divided by 64, which is the prescaler, times the maximum count, which is 256 for the 8-bit timer, and that would be 976, which means basically 976 pulses per second. Now let's look at the same calculation, but for our 16-bit timer. The frequency is going to be equal to 16 million, again that's the speed of our timer, divided by 64 times 65,535, which would be 3.8 hertz or 3.8 pulses per second. So basically that's how you would set up your frequency, how many pulses per second. So now let's talk about duty cycle. Let me try to explain what is duty cycle. So let's start showing you the obvious. This signal is a continuous 5 volts. The voltage sensed by the external device, of course, is 5 volts. So let me show you a different figure. Now, the voltage sensed by the external device is 2.5 volts. So let me try to explain it. Let's start by describing the signal. So 5 volts half of the time and 0 volts the other half of the time, which means 50% of the time on and 50% of the time off. So we start with 5 volts. Now, then we go to 0, and the period is 10 units. We have 5 units, the signal is 5 volts, and 5 units, the signal is 0 volts. So let's talk about duty cycle. So duty cycle is equal to the time on divided by the time on plus time off. Now, time on and time off are percentages. So in this case, the duty cycle would be 50%, which is the time on, divided by time on, which is 50%, plus time off, which is 50%, and that gives us 0.5. Now the equivalent voltage, which is the voltage the external device will sense, is equal to output voltage times duty cycle. So the equivalent voltage in this case would be 5 volts times 0.5 equal to 2.5. What I'm saying is the voltage sensed by the external device is 2.5, and this is how we calculate it. So let's look at another example. Now in this case, the voltage sensed by the external device is 0.5. That means that this device thinks it's getting a 0.5 volts, or it's getting a 0.5 volts as far as the device is concerned. So let's look at the signal description. So what we have here is 5 volts for 1/10 of the time and 0 volts for 9/10 of the time. So that would be 10% of the time is on and 90% is off. Let's look at the figure. We have 5 volts for 1 unit, and then we have 0 volts for 9 units. So 10% of the time on, 90% of the time off. So let's look at the duty cycle. Duty cycle, like I noted before, is percentage time on divided by percentage time on plus percentage time off. So the duty cycle in this case would be 10 divided by 10 plus 90, which is equal to 1/10, which is 0.1. So the equivalent output, which is output voltage times duty cycle, would be 5 volts times 0.1, which would be 0.5. Now this is the important thing, this statement down here. By changing the duty cycle, we can change the voltage sensed by the external device. By using this technique, we can output any voltage between 0 and 5. And we'll have an example that we're going to do that exactly. So let's see how we program these things. So now let me try to explain how we're going to go about setting up the registers to obtain the pulse we want according to the duty cycle we need. So let's see how to configure the duty cycle. So let's start by setting a y-axis and an x-axis. In the y-axis, I'm going to have the number of ticks, and on the x-axis, I'm going to have time. So now the y-axis, I'm going to go between 0 and 255. And I'm putting a line up here as reference, that where's the 255 line. Now this line represents the number of ticks by the 8-bit clock. So basically it keeps increasing till it reaches 255. Now when it reaches 255, the counter is the maximum value of the counter. And basically at this point what's going to happen is going to overflow and it's going to go to 0. So here I'm showing it goes to 0 and then it counts again. And then it does that over and over. So now this is internal to our setup. Now I'm going to set up an X and Y axis here. But what I'm going to put out, what they are going to represent, where the y-axis I'm going to go between 0 and 5. And this is going to represent the output voltage of our microcontroller, which is port D6, and the name of that port when we're dealing with PWM is OC0A in this case. And the x-axis is going to be times. So we have output voltage for the microcontroller and time. And I'm going to relate it on how we change the behavior of the output using our timer. So here in the timer, I'm going to put a mark here which is going to be the output compare value. So we select this particular point as our output compare value. That means that when the timer reaches this value, something is going to happen. So let's see what that is. So our voltage starts, our microcontroller starts putting out 5 volts. Now, when it reaches the output compare value, the output is going to go to 0. And it will remain in 0 after we reach the overflow value, which is going to be 255. So it starts on 5 volts. As soon as it reaches the output compare value, it goes to 0. It remains 0 until the overflow of the counter, I could say the maximum value of our counter. So you can start getting an idea. If I change the output compare value, I'm going to change the amount of time the signal is on and the signal is off, which basically just sounds like our duty cycle, of course. And it's our duty cycle. So let's do another one. So we start again in 5 volts. Then when we reach our compare value, then it goes down to 0. And it remains 0 until it reaches the overflow value, and then it repeats itself. Again, output compare, and here. Now, so if we want to put out this value, then we're going to have to configure our output compare value to the correct value. So when it matches the clock, the signal goes from high to low. So the period of the signal is going to be between our clock going from 0 to its overflow value, max value. The time on is going to be between 0 and the output compare value, the time on, and the time off is going to be between the output compare value and the overflow. So now let's talk about our sample program. Sample program 1, let's see what we're going to do. So we're going to increment the brightness of this light using pulse width modulation. So basically increasing the voltage by changing the duty cycle. We're going to increment the duty cycle until maximum brightness is achieved. So we'll go from 0 to 100 duty cycle, and we'll go from off all the way to the brightness. Once the maximum brightness is reached, we restart from 0. So we increment to the maximum brightness value, then we turn it off, and then we do that again. We're going to use the 8-bit timer. So we need to figure out, okay, when are we going to increment our timer, and how do we know when to increment it? So what we're going to do is we're going to increment our duty cycle each time we get to an overflow. So how do we know that we're in the overflow? Well, we're going to initialize our interrupt to trigger on overflow. So when the interrupt gets to overflow, then we hit we're going to set up an interrupt, so we hit the interrupt service routine, and that's where we're going to increment the duty cycle from 1% to 100%. And the duty cycle is to be recalculated each time we increment, each time the interrupt is incremented, I'm sorry. So let's get going. So don't forget what I'm saying is we're going to set up our timer. So every time we get interrupted, we increment the duty cycle. So let's get going with our sample. I'll start by giving you a global description of the program. So we have here a routine in PWM, which is going to configure the pulse width modulation. Next, we have a init interrupts. This routine will enable the interrupt. So every time we hit the overflow, an interrupt gets triggered. Then the main routine is going to initialize whatever needs to be initialized, and then we'll have a interrupt service routine, which is going to increment the duty cycle each time this interrupt service routine is hit. The processor will use pin D6, port D6 as an output for the PWM signal. Now the port D5, the name of the signal when we're dealing with PWM is OC0A. Now these two lines of code, what they're going to do is the following. They're going to set the microcontroller in such a way that when a match number which we have to define matches the timer, then the signal from the OC0A is going to go low. And this signal will remain low until we hit the max number, which is the overflow. In this case, it has happened to be 256. So when we hit the 256, the overflow number, the timer will go to 0. An interrupt will be triggered, which we are going to configure in a moment. And the output from the OC0A port is going to go high. So we are high till we hit the matching number, then we go low, and we stay low until the max number of the timer. And then again we go high. That's what we're setting with these two lines of code. Next, we are going to configure for the waveform generation mode to be fast PWM. And these are the 3 lines of codes that will do that. Now that's the fast is the most accurate, so that's the one we're going to use. And finally, we're going to set our scaler to 1, meaning that the frequency, because the scaler is the one that controls the frequency of the pulse. So the formula says the frequency is equal to the clock speed, which is 16 million ticks, divided by the maximum number of our clock, which is an 8-bit clock, so that would be 256 times the scalar, which is 1. So that gives us 62,500, which means the pulse width modulation signal is going to have a frequency of 62,500 pulses per second. So let's go now to our interrupt routine. So we're going to set the interrupt on overflow for the timer. This means that basically once we get to the max value, that will trigger an interrupt, and then it goes back to 0. So the reason we do this is because what we want to do is every time the timer gets to the max value, we want to go to the interrupt service routine, where we're going to change our duty cycle to increment it, which is going to increase the brightness of our light. And eventually we get to the max value, then we go to 0 and start over. So next, let's get to the main program. So 2 things we're doing here. We're going to initialize the interrupt, initialize the pulse width modulation. So finally, let's look at the interrupt service routine. And so first thing it does when we get into the interrupt service routine is we increment the duty cycle. Then we ask, hey, did we get to the 100% of the duty cycle? If the answer is no, then we go ahead and calculate the duty cycle with this number. So the duty cycle, which is going to go on the OCR0A, which is the matching number, is going to be the X duty cycle number that we've been incremented, divided by 100 to get the percentage, and multiplied by max value, which is 255. Now, by the way, this max value has been defined here in the to make it a global parameters. Next, we wait 200 milliseconds, and then we go back to the routine, which would be the infinite while. Now, eventually, we're going to get to the point where the X duty cycle is going to be greater than 100. In that case, we go to 0, which basically turns off the LED, and then we start all over again. So let me recap. So we have the routine which is going to initialize and configure everything associated with pulse width modulation. Our signal is going to output from the controller in port D6.
the name of that port when it deals with pulse width modulation is OC0A. Next, we have an interrupt which is going to be triggered every time the counter gets to its max value and it has an overflow. And when that interrupt triggers, that's going to increment the parameter, which it does in 5 and 5, and that's going to increment the value, the duty cycle, and that's going to increment the brightness of our LED. Once we get to 100%, then we do that again.
Okay, with this we're done with the PWM. Let's start talking about the input capture. The input capture, the feature is used to measure the timing of external events. It can be configured to detect the change on port P, ICP1. Now we can capture on the signal in a rising edge, or we can capture on a signal falling edge. So our microcontroller is hooked up to some kind of sensor, and if we can program it in such a way that if the sensor goes from high to low or low to high, we can capture the time when that happens. When the pin detects a change in the input, the current value of the timer is captured and stored on the ICR1 register. Now the capture value tells you the exact moment when the event happened. So if you're interested to know when this happened, well, you use input capture and you'll know exactly when that happened. It is useful for measuring the time between events. So if you want to know how often this particular event happens, then you can use input capture. It also allows the microcontroller to automatically record the timing of an event without needing constant attention from the CPU. So if we didn't have input capture, then the CPU would have to constantly be polling to see, hey, did this happen? So let's look at our example number 2. So this is the schematic. We're going to have a LED hooked up to port PB1, and then we're going to have a switch hooked up to port PB0, which is our ICP1, our input capture pin. Or I should say, it's a pin that can be configured to input capture. Now what we're going to do in our sample problem. So we're going to detect when the push button is pressed. Detect when the push button is released. If the button is held down for more than 2 seconds, then we'll toggle our LED on and off. So we capture the time when it was pressed, we capture the time when it was released, and if it's more than 2 seconds, then we turn the LED on or off. Another way to doing this is I capture when the button is pressed, I set the time to 0, then I capture when it's released, and if this number is 2 seconds, then that means that I can turn on and off the LED. So let's do some preamble calculation, because we need to figure out how many ticks is 2 seconds, because that's what we're going to have to compare. Okay, calculate the number of ticks in 2 seconds. So we're going to use the 16 megahertz clock. So it would be 16 million ticks per second. So 2 seconds is going to be 32 million ticks. So let's try to calculate our prescaler. If I divide 32 million by our max value of our clock, that gives us 488. So we need to select a pre-scaler which is closest to 488, and that would be the 1024. So recalculating everything, that means that 2 seconds has elapsed if the counter gets to 31,250 with a prescaler of 1024. So that's what we have to program to. So let's look at this thing. Let me set up my pointer. So when we have an input, we have an internal pull-up resistor, which means that when the switch is open, the signal will be positive, will be 5 volts. So it's the button is open. When we press the button, the signal will go to low, and it will remain in low until we release the button. So let's see how we would program this. So the signal is high, and we want to know when the button is pressed. So the signal is high, and when we see a falling edge, the signal going from high to low, we know that somebody pressed the button. So what we are going to do is we're going to go from here when we sense the falling edge. So I should say first we're going to configure so we sense a falling edge. So once the falling edge is triggered, then we're going to go to a interrupt will be triggered. And what we need to do in the interrupt service routine is we need to reconfigure our input capture to go from falling edge to go to rising edge. So we configure it here, and then we're going to detect when the signal goes from low to high, and we're going to capture the time at this point. So being able to capture when it goes from high to low, which is falling edge, reconfigure it, and being able to capture the time when it goes rising edge, that means from low to high, that's going to give us 2 time that we can use to calculate whether or not 2 seconds have elapsed, and if 2 seconds have elapsed, then we can turn on or off our LED. Let me start by giving you a global view of the program. So we have a routine for initializing the port. We have a routine for initializing the timer. Then we have a couple of routines, one for enabling and disabling the global interrupts. Here we have the main program, which basically initializes whatever needs to be initialized. And finally, we have our interrupt service routine, which is going to be triggered by a input capture event. Let's start by looking at the code in the init ports. So this first line of code, what it does is sets the pin B0 to input, and that pin is called the ICP1. Now we have a switch hooked up to that pin, therefore we need to set up a pull-up resistor. The reason for this is that we always want to make sure that we have a known state when we have a switch. Next, we're setting up the port B1 to output. That's over that port we're going to control the turning on or off of our LEDs. Now, before we can review the init timer, look at the code, we need to first do some calculations. So this program, an LED would be toggled as long as a button has been pressed for 2 seconds. So we need to figure out how many ticks it takes for 2 seconds. So our crystal is 16 million ticks per second. Therefore, 2 seconds are going to be 32 million ticks. So after 32 million ticks, we know that at least 2 seconds have elapsed. So let's try to figure out our prescaler, because 32 million doesn't fit in our 16-bit register. So the first thing we do is we take, as usually, we take the 32 million and divide it by the max value of our register, 16-bit register, which is 65,536. And the result is 488. So based on that, we select the prescaler closest to this number, which would be the 1024. So what we do next is we take our 48 million ticks and divide them by 1024, and that gives us a number of 31,250. So we know that if 31,250 ticks have gone by, that means that 2 seconds has elapsed. We say a prescaler of 1024. So let's look our detailed code in the init timer. So these 2 lines of code, what they do is set up the prescalers to be 1024. Now we need to configure for input capture on timer 1. So what we know is that we're using a pull-up resistor. So that means the first, when somebody pushes the button, the signal is going to go from high to low. So what we need to do is we need to configure the input capture to go on falling edge from high to low, and that's what this line of code is doing. Next, we enable the interrupt, so when the input capture from high to low happens, that would trigger an interrupt. And finally, we set up the timer to 0. Next, these 2 routines are just setting up the global interrupt and disabling the global interrupts. So let's get into our main routine. So the main routine calls the init ports, which is going to initialize the ports, calls the init timer, which is going to initialize the timer for the capture, and finally it enables the interrupts. Now I added these 3 lines of code. What this does is this line of code turns on the B1 LED, hooked up to B1 I should say, delays for 1 second, and then it turns it off. So basically what I want is when I apply power to the card, I want a light to come on and off like a heartbeat that it tells me things have been turned on. Now before I get into the code associated with the interrupt service routine, I would like to mention that there are 2 variables that I define globally, and this is the button press and duration. These 2 are volatile, and they are going to be used on the interrupt service routine. So let's look at the interrupt service routine. So when it gets triggered the first time, so the signal goes from high to low, falling edge. First thing I do is I have to wait for 10 milliseconds, and that's to debounce the switch. Now, how I got to this number is by experimenting. I made experimentation and I realized that if I wait for 10 milliseconds, I can get rid of all the debouncing issues. Next, I disable the interrupt. I want to make sure that I don't get interrupted when I'm inside the interrupt service routine. Now, my first question is, I ask, is the button equal to 0? That means that the button has been pushed, because I start here from 0. So I ask, did the button get pushed? And if it's 0, that means that the button had actually got pushed. So the first thing I do is I change the capturing from going from falling edge to the reverse, which we from rising edge. So when you push the button, it went down, and then now what I want to detect when it goes up again. So I set up to rising edge, then I set up the button press to 1, meaning that the button has been pressed, and now we should be looking at the press. And then I set up the timer to 0. The idea here is, okay, I set up the timer to 0. So when the button is released, I'm going to come back to this interrupt service routine, but I'm going to end up in the else. So let's look at the else. So the first thing I do is I capture the time, the number of ticks that has elapsed since the time the button was pushed. Because when you push the button, I set up the timer to 0. So when you come back that you release the button, it's going to give me how long it took for you to release the button. So then the next thing I do is I say, hey, is duration greater than 31,250, which is the number of ticks? That means that at least 2 seconds have elapsed. If the answer is yes, then I toggle the button. And after toggling the button, I set up the duration to 0. I change the capture to do from falling edge, from low to high. That's this line of code. I go back to button has not been pressed and set up the timer to 0. And finally, before going out of the interrupt service routine, I enable. So let's recap what happened. You push the button and the signal goes from high to low and we end up in this area of the routine. So here what I do is I say, hey, I'm going to set up the time to 0, and I'm going to say that the button was pressed. And then when the button gets released, I'm going to end up here in the else, and I'm going to check how much time has elapsed. Okay, with this example, I conclude the input capturing section. Let me start by giving you a global view. Okay, a little bit of technical problem. So summary. So this dealt with timer and counter sample programs. I talked about pulse width modulation. I gave you some definitions, explanations, and also a sample program. And also address input capture, where again I gave you some definitions and also an example program. So I hope you have enjoyed this presentation, and I'll see you in the next presentation. Thank you very much.